So this is a talk about agent-based systems in artificial life as well as adaptive systems. So if you go into this link on top, thinking, feeling, acting, search.sh, you'll be able to see the this whole thing in action. Also, the code is available on GitHub. This is slightly different from what I'm presenting today, but I will fix things up and upload. So this is the basis of all these things. And activism is that the intelligence or the cognition comes from dynamic interaction between an agent and its environment. So there's this thing about intelligence these days that any machine learning algorithm is need to be an artificial intelligence. But I kind of take a different view of it. Artificial intelligence is, or intelligence is something that arises from interaction between an agent, its brain, its body, and the environment. Somewhat also dependent on the observer as well. Going on to the next slide. So the intelligence, it's a very difficult thing to sort of quantify. But for things like computational methods or computational problems, we can define it as intelligence is how successful you are in a given environment. So this is not coming from something something I made up. It's just it's the definition that people who research on general artificial intelligence, like people like Marcus Hutter or Shane Legg from DeepMind, they are the people who would define this as this way. So in this little experiment, I have a little spaceship that goes through this environment which is filled with asteroids or obstacles. Going into the next slide. So the environment is filled with obstacles. It changes in every generation. I would define what a generation is. If the spaceship collides with one of the obstacles, or if it goes out of bounds, then the game will be over. Success of the agent is not monitored in power, it's the horizontal distance and travel. Going to the next slide. So the body of this agent has 5 distance sensors. It can control where it is looking. So there's a 360-degree rotational view, as well as the view span it can control. Also, it can control the velocity, horizontal and vertical velocities. Also, it has some amount of energy for it to consume. So each of the action, like movement, consumes energy. This is the composition of the. Let's look at what brain of this whole system is. So going into the next slide. The brain is it's a 3-layer feed-forward network which has 5 inputs and 10 nodes in the hidden layer and 4 nodes in the output layer. So 5 nodes, these are the 5 sensory input that comes in from the distance sensors, goes directly into the hidden layers, and then output is the velocity and the sensor directions and the view angle of the sensor. Going into the next slide. So now we have discussed what is the whole environment, the body and the brain, all these bits, and then we are putting them together, and then we train it using evolutionary algorithm called genetic algorithms. I think you may have heard of this. This is quite popular these days in every high schooler would use this sort of algorithm to optimize them. So the training starts from, for each of the agent, we take one agent and then it starts at a random horizontal, vertical location, and then we run the game for two sessions or multiple sessions you can. The idea is that by randomizing the vertical position, we reduce the likelihood that the successes or the failures are due to randomness. So we have result. Each of in each generation we randomize the and also the fitness is computed as the horizontal distance that the agent has traveled. You could also take the time it was alive as well. For this experiment, I will use the horizontal distance. If you look at the experiment, you see two graphs. One is for median fitness. The other one is for max fitness. The median fitness shows that in each generation the population becomes better or worse. Max fitness is the agent that is best for in each of the generation. Going to the next slide, you can see how the feed-forward network is defined. So the good thing about Fable is that you can write in Sharp and then quickly generate HTML, JavaScript, and then show it to people very quickly. So this is in contrast with all the other methods that I tried out, like Qt or any other GUI framework. Is very cumbersome and difficult to also tried out it's like type and then TypeScript is good, but it is so much more verbose than this. Elm has a problem of generating large number of random numbers. So Fable has the best of both worlds, where I can call up JavaScript functions for various different things, as well as have the functional with the Sharp. So a feed-forward network, it's a very simple way of defining this. Each node is composed of a bias value and a list of weights, and each layer is composed of a number of nodes, and a network is a number of layers. So this is a very, very hierarchical way of defining this, and with F# you can quickly put these two together. Going into the next slide. So here we've defined what the computations are. In order to compute the network, we have to first compute the nodes, and then the layers, and then the whole network. So this whole thing flows really well. First, in the first few lines, you define how the inputs are multiplied with the weights, and then sum together, and then you add the bias value, and then this goes through something called a sigmoid. The whole purpose of the sigmoid is to map out a large range of values, like from minus infinity to positive infinity, to a small range of value, like minus 1 to minus positive. So this sort of nonlinearity gives you the intelligence of a network. So in each layer, you compute all the nodes in that layer, and then for the network you compute the layer. So this whole thing flows really well. So going to the next slide. Once you compute the feed-forward network, you get some value. This is the output of the network. And this can be used for various different actions. So, for example, mode actions. So Vx here defines the horizontal velocity, and Vy defines the vertical velocity. So the Z values, you get 4 values here in this network. So 0 and 1 is mapped to these velocities, and then the rest of the values are mapped to the field of vision where it is looking, and so on. It is kind of important to add this random noise into these variables. This is mainly because when you model an actual system, the sensors itself has some amount of noise. Also, the motors have some amount of noise. So, adding this, modeling this randomness is quite useful as well. The gains are it's a multiplicative value that can increase the output we get from Z values. This can be evolved using the genetic algorithm, or you could just use a static value. Next slide. So, so the genetic algorithm does all the training. So what it does is that it has an array of floating point values that maps to various variables like weights, biases, and gains. And we use the standard genetic algorithm operators like the mutation and crossover in order to select the best agents. What we do is we shuffle the population and then hit the first half against the second half, looking at their fitness. So the fitness, as we defined earlier, the fitness is the horizontal distance we travel. So the losing agent will get some amount of bits from the winning agent. This is the whole idea about the standard operators of genetic algorithms. So let's go and take a look how this actually works. So if you go into the next slide and then click on the menu. You can see that these agents are kind of struggling. So this is the generation 0 of the agent. It doesn't know how to move. It doesn't know where to look. It's moving about, but it doesn't have any idea what's going on. So in here you can see that the agent has somehow figured out how to move horizontally. Also, it's vigorously scanning the area, but doesn't really have an idea how to avoid the obstacles. So let's look at the next video. That it's so this is the video just you saw just now. It's after 74 generations. So this takes a little while for it to figure out everything, but if you go into demo 3, okay. So now you can actually see that it can very well avoid the obstacles. It knows how to scan the environment, and also it associates that these are also things that it has to avoid. So after a while, without us. Here you can see that it is actually avoiding obstacles. It has learned how to sense the sensors properly, and also it has control of the horizontal and vertical velocities. So as you can see, that these are all discovered behaviors. We didn't specifically teach them teach the agent how to do these things. It was all emergent properties of the whole system. So this is the kind of things that you can do with this sort of enactivism based agent-based systems. Okay, so that's pretty much we're at the end of the whole talk. So this can be improved. This is a project that I've been doing some time ago, and right now I'm having less and less time to devote to it. But if you guys are interested in playing around with these things, the code is available at this location. You can improve this with an RNN. I have only used a feed-forward network for this one. The good things about RNN is that it gives the agent some amount of memory, and also the control system is much more smoother. We could also improve this with having more constraints and then rewards. Also, probably you could use some sort of some other task for the network to learn. For example, right now it can do two things. It can learn where to look, also how to move. Maybe we can give it a gun and then shoot the asteroids as well. So yeah, that's all I have. If you have any questions, I can answer depending on the time. I'm not using any modules apart from what I have coded in the code over there, actually. So even the vector classes I have coded myself. So might not be optimal, but this is something I want to have some sort of a full sort of control over. So yeah, everything is coded in the file itself. If you go into github.com rnnbot, you can see all the code there. It doesn't use any other libraries. So some of these so if you start it now, it takes about a day for you to see something interesting, actually. So that's one of the things about running this on the browser, because I'm only running one agent at a time. So one thing probably someone can do is to parallelize the agents and run the whole generation in just one go, rather than one after the other. So this will give you a good speed up. But it takes a little while. I mean, this sort of thing, these are generational optimizations, so this takes quite a long while. One other thing that someone can do is to not use genetic algorithms for optimization. They could use something like backpropagation, which is much more efficient. But in most of the agent-based systems, people opt to use genetic algorithm because it looks cooler with the the bio-inspired theme. So perhaps someone can write a text generation tool, so like a conversational robot. So this is again some sort of optimization, but I think an RNN would be much better because it has memory for text generation. It's better to have some sort of memory, like an RNN. genetic algorithm is itself is a optimization method, so it can be used for various things. Mostly about control systems that we use in agent-based systems, but you could use it for anything. It's so general purpose. Thank you.